now. Ever felt like the Navier-Stokes equations are a black box? Total energy is bounded, yet things can still blow up at tiny scales. How? That's the million-dollar question, literally. Today, we're cracking it open with a new lens, DI-KWP mesh. So, what's the magic trick? It's called bidirectional co-origin scale transfer closure, or BCSTC for short. Think of it like this: energy doesn't just vanish, it moves. A loss here is a gain there, same source, different scale, maybe different phase. The HM weight difference. Just a different way of looking at the same transfer, not some sneaky new energy injection. And crucially, the leftover stuff at high frequencies. It gets eaten by viscosity. Mathematically, we say the high-scale closure coefficient beta sub m comma q of t goes to 0 as q goes to infinity. Simple, right? Almost. How do we actually make this happen? Through the DIKWP protocol, think of it as our proof's DNA. P registers the input-output pairs. D says donor loss and receiver gain are one and the same transfer. I captures the scale and phase differences. K builds the complete packet, everything involved, including viscosity. Is strict, no orphan outputs, every effect must have a registered cause. And P ensures everything replays correctly. This chain reaction means the messy high-frequency bits get absorbed by viscosity, keeping our HM norm in check. It's like having a super-efficient recycling system for energy transfers. Okay, let's trace the logic. First, we meticulously register every single energy transfer using that P to D to I to K to W to P cycle. Then the low-frequency stuff? Easy peasy, controlled by total energy. The real action is at high frequencies, where BCSTC steps in and closes the gap relative to viscous dissipation. Finally, we apply the trusty Gronwall inequality, and boom, the H norm stays bounded for any finite time t. Since t was arbitrary, the solution keeps going smoothly forever. No breakdowns allowed. Now, before you get too excited and claim we solved the Clay Millennium Prize, hold on. This isn't just running simulations on a fancy grid. We're talking about semantic closure, ensuring every high-frequency output has a complete provenance. The big hurdle: proving this works perfectly in the classical limit that those high-scale transfers keep their phase, direction, and identity without creating weird defects. Our demo shows it works beautifully on a 32-cube grid, with residuals tiny enough to make an astronomer blush. But the final stamp of approval? Still pending from the wider mathematical community. So, what's the big takeaway? We've shifted the focus from just measuring how big the waves are to tracking who is responsible for each wave's journey. BCSTC is our key to taming those high-frequency transfers within the Mesh 8.0 framework. The next frontier, bridging this to classical analysis. If that bridge holds, global smoothness for Navier-Stokes might just be within reach. Food for thought, isn't it?